And a lot of what we've done up to this point has been just kind of definitions. We're just laying the groundwork. What is energy? How do we talk about it when a chemical reaction requires energy from the surroundings in the form of heat, or gives off energy in the forms of heat, and kind of vice versa. How do we keep track of all of those things? So what we've done so far is mostly just definitions and laying the groundwork. And we'll continue that a little bit here with a few more definitions. So one is, one of these definitions that's commonly used is the term state function. Now, a state function is simply any property whose value is path independent. What does that mean? It means that it doesn't matter how we got to that point, whether we just went directly to that point or if we did some very circuitous pathway and finally ended up at that point, that the value of that property is the same at that point, regardless of how we got there. So internal energy is an example of a state function. Let's sort of show a brief example of this. So let's just consider the internal energy of some system. And internal energy, as we'll find out later in chapter 10, is directly related to the temperature of the system. So those two are directly related. So if we think about starting out with ice water, so it's at 0 degrees Celsius, I've got 50 grams of it, and I just let it warm up. It's taking energy from the surroundings in order to raise the temperature and melt the ice, but eventually it all melts and the temperature raises to 25 degrees Celsius. The energy of 50 grams of water at 25 degrees Celsius is a certain value. Now let's say that I started out alternatively with 50 grams of boiling hot water, and I just let that cool down all the way down to 25 degrees Celsius. So I start out at 100 degrees Celsius, and then it finally cools down to be 50 grams of water at 25 degrees Celsius. The internal energy of that 50 grams of water at 25 degrees Celsius is the same as the internal energy of 50 grams of water at 25 degrees Celsius that started out as frozen ice cubes. So it doesn't matter how we got there. The internal energy at that particular temperature of that particular mass of water is the same. And so it's thus path independent. Now, there's another term known as enthalpy, which is also a state function. And this is useful for us, and we'll sort of see why in a little bit. So what is enthalpy? Well, enthalpy is given the symbol H, and it is the total heat content of a system at constant pressure. So if we've talked about internal energy being the sum of the heat, Q, and the work, W, as long as we're at constant pressure, then enthalpy is simply the total amount of heat. So we're really focusing just on Q here at this point. And enthalpy also happens to be a state function, so it doesn't matter how we get to a certain value. The enthalpy at that point is independent of how we got there. So just a brief definition here. H is equal to Q with a subscript P, just indicating that we're at constant pressure. Now, the change in enthalpy allows us a measure of energy changes during a reaction. Many reactions do not result in significant amounts of work being done, and so enthalpy really, the change in heat then gives us a measure of the change in internal energy. Let's go through some examples and some features of enthalpy. If you're confused, I will try to clarify this as we go along. Stick with me. So the change in enthalpy is just like the change in internal energy. It's the enthalpy of the products minus the enthalpy of the reactants. And so if delta H is negative, then that's the same as Q being negative, as we talked before. So this is an exothermic reaction. If delta H is positive, then the change in Q is positive, and it's an endothermic reaction. And so here's sort of an example of a hydrogen balloon igniting and reacting with oxygen. So my starting, the energy or the enthalpy of the hydrogen and oxygen molecule starts out at some value, but then when I go to water, the enthalpy of water is at a lower value. And so the change in enthalpy then is negative because it's products minus reactants, and thus I have an exothermic reaction. Now, in this case, I can quantify the actual amount of energy. So and we'll explain how we kind of do this in a moment, but here we've got the enthalpy of my water as a gas turns out to be negative 241.8 kilojoules, and there's two of them. So that's the total amount of enthalpy of my products. And it turns out that the enthalpy of my starting materials actually started out at 0 energy. And we'll explain later on when we get to heats of formation why that is. But I can calculate then quantitatively and say that the change in enthalpy for this reaction is negative 483.6 kilojoules. In other words, 483.6 kilojoules of energy is given off by this reaction, as you can see by the cloud of flame and the change in heat. So some notes on enthalpy that will be helpful. First, that enthalpy is an extensive property. We haven't talked a lot about intensive and extensive properties, but extensive property is one that depends on the amount. If something is extensive, it depends on the amount that is present. So mass is an extensive property. How much mass you have depends on the amount of the substance. Intensive properties, on the other hand, are independent of the amount of mass. So temperature, for example. If you have 100 grams of water at 25 degrees Celsius, it doesn't matter whether you have 25 grams or 100 grams. The temperature of the sample isn't dependent on the amount that you have at all. So that would be an intensive property. However, enthalpy, which is the amount of heat at constant pressure, that is an extensive property. It does depend on the amount of substance that you have present. So for example here, 1 mole of O2 in the last reaction produced 483.6 kilojoules of energy. And that actually allows us to write a new conversion factor. So we can relate the moles of a reactant to the amount of energy that's produced. But the point here in this specific example is that enthalpy depends on the amount. So if 1 mole produces 483.6 kilojoules of energy, then 2 moles of oxygen will produce 967.2 kilojoules of energy in that particular reaction. Delta H for a reaction also depends on the physical states of the reactants and products. So producing water vapor, as we did, gives off negative 241.8 kilojoules per mole, whereas producing liquid water produces a different amount of heat, negative 285.8 kilojoules. And that heat difference corresponds to the energy required to do the phase change between liquid water and water vapor. But it's really important to note that there is a difference between between physical states. The physical states do impact the amount of heat present, or enthalpy. Finally, the change in enthalpy for a reaction if we write the reaction in reverse, then the change in enthalpy is simply the negative value of the amount for the forward reaction. Now, you might be confused. Why would we want to write a reaction in reverse? It will make a lot of sense when we talk about Hess's law. But for now, simply note that if we write the reaction in the forward direction and we get some enthalpy value, then the enthalpy value for the reaction written in reverse is the exact same numerical value, simply with the opposite sign. Now, we can use enthalpy of reaction as another equality or another conversion factor. So let's go through an example here. How much heat is produced from burning 12.2 grams of hydrogen gas in a constant pressure system? And we're given the chemical equation, as we showed earlier, with the corresponding change in enthalpy for the reaction. Well, what I can see from this is that the balanced chemical equation gives me the amounts of reactants and products in moles. And I can relate the number of moles of any substance to the amount of enthalpy, to the change in enthalpy for the reaction. So I can say that 2 moles of hydrogen in this reaction produced 483.6 kilojoules of energy in the form of heat or enthalpy. So 2 moles of hydrogen is proportional to negative 483.6 kilojoules. That is now, that's now a proportionality or an equality. We can use it as a conversion factor. We can say, oh, 2 moles of H2 in this reaction equals, because it produces, negative 483.6 kilojoules. So if I want to know how much heat is going to be produced from burning 12.2 grams, well, if I can find out the number of moles of hydrogen, then I can use the relationship between moles of hydrogen and enthalpy to cancel out moles of hydrogen and find the final enthalpy value. So here, 12.2 grams of H2. I convert that to moles by dividing by the molar mass here. So moles on top, 2.02 grams on bottom. And then I have this relationship between moles and enthalpy. So I arrange it so that moles is on the bottom to cancel out. And I've got my enthalpy value on top. I multiply everything through, the grams cancel, the moles cancel, and I'm left with negative 140, or negative 1.46 times 10 to the third kilojoules. That's the amount of energy then, the 1.46 times 10 to the third kilojoules, that's the amount of energy that would be given off. The negative sign indicates that it's given off. And this is how I can use enthalpy of reaction as a conversion factor. Let's do one more example of this, just worked out. So the complete combustion of ethanol, which is shown here, and we're given the molar mass, proceeds as follows. So you've got ethanol as a liquid plus 3 moles of oxygen produces 2 moles of CO2 and 3 moles of water as a liquid. And the change in enthalpy for the reaction is negative 555 kilojoules. So what is the enthalpy change for combustion of 15.0 grams of ethanol? Well, what I need to do is I need to relate moles of ethanol to my enthalpy. And I can do that using just this balanced chemical equation. So if I write here 1 mole of C2H5OH is proportional to negative 555 kilojoules. So if that's my proportionality, I can use that as a conversion factor. What I need simply is to find the number of moles of ethanol and then use this conversion factor to find the number of kilojoules that would result from that number of moles. So if I start with 15.0 grams of C2H5OH and use the molar mass, 1 mole of C2H5OH over 46.0 grams of C2H5OH. That will now cancel out my grams. Now I've got moles, and so I can use my relationship above as a conversion factor, so negative 555 kilojoules per 1 mole of C2H5OH. And that cancels out, and I can multiply through and determine the number of kilojoules. So if I multiply this through, pull out my calculator, 15.0 divided by 46.0, and then times negative 555, I come out with a number here that is negative 180.978 kilojoules. And then I just have to go back and keep track of my number of significant figures. I should only have 3 significant figures. So I'm going to have to round this to negative 181 kilojoules. That is then the amount of heat or enthalpy that is given off during this combustion reaction.